Welcome to qnawire.
Hi everyone, so what we have is a turbine that is powering a compressor and also a generator. So steam is entering this turbine from 3 to 4, and we also have some air that is going from 1 to 2 through the compressor that's being compressed. What we're asked to solve for is to solve for the net power that is going to the generator. So the first thing we're going to do is actually go ahead and write down our assumptions. We are going to assume this is a steady state process, so properties will not be changing with time. We're also going to assume that any changes in kinetic energy, any changes in potential energy, and any changes in heat and heat transfer are going to be equal to 0, because we do know that everything is adiabatic. And we're also going to assume that air is an ideal gas with variable specific heats. So what we're going to do is, we know that our initial condition going into the compressor is going to be having a pressure equal to 12.5 megapascals, and that's also going to have a temperature equal to 500 degrees C. And from this we can deduce that we have an enthalpy equal to 3,343.6 kilojoules per kilogram. And at P4, so the exit state of our turbine, we have a pressure equal to 10 kPa and a quality equal to 0.92. And from this we can deduce that our H4 will be equal to HF plus X times HFG, and this will give us an enthalpy at the exit of the turbine equal to 2,392.5 kilojoules per kilogram. From the air table, we can then deduce that with an input temperature into the compressor of 295 Kelvin, we can say that the input enthalpy into the compressor is 295.17 kilojoules per kilogram. Similarly, with the exit temperature known of 620 Kelvin, this gives us an exit enthalpy equal to 628.07 kilojoules per kilogram. Next, what we're going to do is we're going to write down our energy balance. So since we are operating at steady state conditions, we know that the rate of change of energy coming into the system is equal to the rate of change of energy leaving the system. So what we're going to do is we're going to take the compressor as our first system, and we're going to say that the work coming into the compressor plus m dot air H1 is equal to m dot air H2. And solving for the work of the compressor, this gives us a W dot equal to m dot H2 minus H1. Now, if we look at our turbine, we see that the m dot steam times H3 is equal to the work produced by the turbine plus m dot compressor turbine m dot steam times H4. Now solving for the work extracted by the turbine, this gives us an m dot steam H3 minus H4. Now what we can do is we can go ahead and plug in for all these components and all for these variables, and we'll see that the work required to drive this compressor is 3,329 kilowatts, and we'll see that the work extracted by the turbine is equal to 23,777 kilowatts. Now the difference in this between these two terms is what's going to power the generator. So W generator is equal to W turbine minus W dot by the compressor. And this gives us a total power output that's going to the generator equal to 20,448 kilowatts. And that's our final answer.